Yeah, I want to go over some of the stuff about cell potential. So let's make a cell. And for a cell, we need usually a solution with metal ions in it. So I'm going to use zinc sulfate, and we'll make it standard 1 molar. And then we need a solution with another set of metal. So we'll make that copper sulfate. Oops. And we'll make that 1 molar. And in the solutions with the metal ions, we'll put the same metal as that ion is. So in this solution, we'll put solid zinc, and in the copper, we'll put a piece of solid copper. And we're going to connect those, and let's just put a meter. Don't do that. Running off of the, or we could put a little motor or something. And then we need some way to keep the ion balance correct. So usually we use what's called a salt bridge. So we want to draw a salt bridge in here. And perhaps we'll put 1 molar potassium nitrate in that. So we can use different salts, but that will be a choice. So that's my salt bridge. And in this, the electrons are going to flow from the zinc and into the copper. So what that must mean, this is this direction they go spontaneously. That means that the electrons must be at higher energy on the zinc than they are on the copper. We could kind of think of that like if we had a pool of water and then a drop off. So here's a cliff. That water is going to flow down hill from the high energy, high potential energy height down to a lower position. So let's let that do that. And if I put a water wheel here, I could see that that water has energy and it can do work. So we'll set a water wheel there that can spin and extract some of the energy from the water. So the same way I can do work with those electrons as they go from the higher energy zinc to the lower energy copper. So electrons have higher energy when they're on the zinc and lower energy when they're on the copper. So they go from one to the other. Now, the cell potential gives me an idea of the difference in energy. So the higher this water is, the faster it'll be flowing, the more work it can do. And so if we consider the energy that, say, a standard amount of water, maybe for each gallon of water, I can get so much energy depending on the height. That's sort of what the cell potential is. So the cell potential measures how much work I can get out, what the energy difference is for a standard number of electrons. So the cell potential, also called the EMF, or electromotive force, the cell potential is measured in volts. And a volt, the units on volts are joules per coulomb. So I have 1 coulomb of charge. If I have 1 volt, 1 coulomb of charge will have an energy of 1 joule. Now remember, an electron has a charge of 1.6 times 10 to the minus 19 coulombs. And this means that in 1 coulomb, there are 1 over 1.6 times 10 to the minus 19, or 6.25 times 10 to the 18th electrons. So the volt says I have 6.25 times 10 to the 18th electrons at I have 6.25 times 10 to the 18th electrons with 1 joule of energy. So let's see where we go from there. In this, this cell potential is an intensive property. It doesn't depend on how much stuff reacts. It's sort of like elevation. You're at the same elevation whether you just went up yourself or you carried a whole pack or a whole bunch of people went up. But the more you take to the higher elevation, the more work you've done, the more potential energy you have. So the more water you have at the high elevation, the more work you can do. But also the higher the water is, the more work you can do. Now, to measure elevation, we usually compare things to sea level. So I could say, well, I started off at 400 feet above sea level and I climbed to 600 feet above sea level. So I had a change in elevation of 200 feet. And both of those are relative to the same, same place. So this is the way we also deal with our half reactions. Remember, we can split the cell up into 2 parts. So let's do it this for copper. So I have zinc giving up electrons to form zinc 2 plus. And that's the anode reaction. It's also oxidation. So that's the oxidation half reaction. And I have copper 2 plus gaining 2 electrons to become copper metal. So that's liquid solids there. And my overall reaction is zinc plus copper 2 plus gives me copper plus zinc 2 plus. And this is the cathode and its reduction. And I always remember which one goes together because anode and oxidation start with vowels and cathode and reduction start with consonants. So what we can do is my overall cell potential for this is 1.10 volts, and I can measure these relative to the same, say, take my zinc as the anode and put it against a different cathode, and take my copper as the cathode, put it against an anode that's the same or reverse reaction as the one I put with the zinc. And if I assign that to be my 0 point, just like sea level is 0 elevation, I can then compare, put those, subtract one from the other and get the overall elevation. So the electrode that we use is called the standard hydrogen electrode. So this is going to be a half of my cell. Whoops. Dangerous to think. Standard hydrogen electrode. Call that SHE. And it's made by having a solution that is 1 molar in hydrogen ions. And then I'm going to use hydrogen gas, which doesn't conduct electricity. So in here we'll put, need to hydrogen gas in. So we'll send that in there. It's going to bubble out of here. And this is 1 molar H plus solution. And my reduction reaction is 2H plus 2 electrons gives me H2 gas. And if this is 1 molar, and this is 1 atmosphere, then the standard potential for that reaction is 0. So the E0 for that is equal to 0 volts. So that's assigned to be 0 in every case. And then what we want to do is cook that up. So let's make make a cell with zinc. So I'm going to put my zinc in here. Here's my zinc solution. We'll make it 1 molar. Here's my zinc. And then we'll make the other piece. 1 molar H plus. Put in my I mentioned this little wire I'm just putting in here is just a platinum wire that doesn't react, but it carries the electrons to the circuit. So we'll set that circuit up. Put in. We still have to have our salt bridge. And in this particular reaction, it turns out that the electrons, the zinc wants to give up electrons again. So my reaction is going to be zinc plus 2H plus goes to H2 plus zinc 2 plus. So that's the overall reaction. The half reactions are, the zinc one is the same as we had before, zinc going to zinc 2 plus 2 electrons, and 2H plus gaining 2 electrons to give me H2. And this one is 0 volts. The overall cell potential for this is negative, so it's minus 0.7. No, it can't be negative. It's 0.76 volts. Just a minute. Okay. Now, the one of the kind of strange things is this is oxidation, but the way they always tabulate this is as reduction. So when you look at the table, it's going to say zinc 2 plus 2E minus gives me zinc. So the E0 for the cell is equal to the E0 for the cathode, which is the reduction part of the reaction. Now this is oxidation, so this is the anode, right? So in this case, the cathode is 0 minus the E0 for the anode. These are reduction. Both of these are written as the reduction. So if this is 0.76, that equals to 0 minus, that must be a minus 0.76. So for this reaction, the E0 reduction, the reduction potential is minus 0.76. So the interesting thing is things with negative values for the reduction potentials are things that the electrons are higher energy on those than they are on the H plus. So when I put them with H plus, they're going to transfer electrons to H plus, and H plus is going to gain the electrons. Things that are positive, the reaction is going to go the other direction. Hydrogen will give up electrons to that. So if I make my other reaction and I put copper in here, so I'm going to make this side copper sulfate, and this is still my standard hydrogen electrode. H2 going in. Didn't write H2 going in here. Let's do that. Salt bridge. Hook this circuit up. And I have, in this case, the reaction is going to go the other direction. So I'm going to have Cu2 plus is reacting with H2. To produce B2H plus Cu metal. So the reduction is the copper, and E0 cell for this reaction is going to be 0.34, and that's going to equal 0.34 minus 0. But the 0.34 goes with that part, and it's 0 both directions. So the even though the hydrogen half reaction, it's going H2 going to 2H plus 2 electrons is the half reaction for hydrogen now, and that makes that the anode because it's oxidizing, it's losing electrons, so it goes over here. It still has a cell potential of 0. So if I go back to my cell with copper and zinc, I have zinc in that half reaction going to zinc 2 plus 2 electrons, and I have copper 2 plus 2 electrons going to copper, and we identified this as the anode and this is the cathode, and this has a E0 reduction of minus 0.76, and this is 0.34. E0 cell is equal to the cathode, 0.34 reduction potential, minus the anode reduction potential, which is negative. So that becomes 1.1 volts when I do the final calculation. Now, I said the cell potential represented an energy difference. Now, if I want to know the energy for this overall reaction, so let's write that. Solids. E0 is equal to 1.10 volts. As this is balanced, let's say it's standard to say we have 1 mole of zinc is forming 1 mole of zinc ions, and 1 mole of copper ions is forming 1 mole of copper. And overall, there are two moles of electrons transferred. And volts is joules per coulomb. So if I figure out how many coulombs 2 moles of electrons is and multiply it by the volts, I'll get the energy. So it turns out free energy is equal to, I have to change the sign because these are if the cell potential is positive, the reaction is spontaneous. But we know that for a reaction, the free energy, for the reaction to be spontaneous, the free energy has to be negative. So this is going to equal to minus the number of moles transferred, in this case 2, times the number of coulombs on 1 mole of electrons times the E0. So for this reaction, that will be minus 2 moles of electrons times the value for this is called the or Faraday constant. I say it's the charge on 1 mole of electrons. That's 96,485 coulombs for 1 mole of electrons. So those are going to cancel. And then that's times 1.10 volts, which is joules per coulomb. Okay, so I'm going to write it that way. That's a volt. So the coulombs cancel, and I'm left with joules. And when I do that, I think I did that calculation, I come out with minus 212,000 joules, or minus 212 kilojoules. So that would be delta G for that reaction, got in from E0. Now I can, it doesn't have to be an electrochemical reaction for me to use this. If anything, I can write the half reactions together. I don't actually have to make the cells. I can calculate from the table what the cell potential would be using the equation, the E0. Let's write it down. E0 equals per cell E0 reduction for the cathode. I guess this would be the best way to do it. Minus E0 reduction for the anode. Some books will write this with the opposite sign and call it E0 oxidation, and then just add the two. But most of the books now do it this way. So we're going to try to follow what your textbook does. Now, another thing that the E0s tell me is, because they're telling me how much energy the electrons are, what things can lose electrons easily and what things tend to gain electrons easily. So things with, if they have a large negative E0 for the E0 reduction, the products of that half reaction lose electrons easily. If they have a large positive E0 reduction, the reactants have a large pull on electrons. They gain electrons. I get energy off when they gain electrons. So I'm going to say want to gain electrons. Now, I always have reduction and oxidation occurring together. So if something easily loses electrons, it tends to give those to almost anybody else that wants them, which causes them to be reduced. So things that easily lose electrons, and these tend to be on the lower right-hand corner of the table on the product side. These cause something else to be reduced. So they're called reducing agents. Now these might be something like sodium or potassium or common, or lithium are good reducing agents. They lose electrons easily. And things that want to gain electrons are oxidizing agents. So silver ions, give me an example, permanganate dichromate. These are all good oxidizing agents, and they tend to be on the upper left-hand side of the table of reduction potentials. And they're the reactants with the large E0 reduction, which means they're easily reduced. And if they're easily reduced, then something had to give them electrons, so they're good at oxidizing other things. So it's a little bit interesting to keep these straight. So I'm going to call that quits on this video, and let me know anything that I didn't make clear for you so we can get that cleared up.